Okay, in this lab you're going to use this setup to experimentally determine the universal gas constant. Now, I want you to notice a few things about this setup. First of all, you've got to keep these tubes and cords free of the hot plate, so I've got it wrapped around the ring stand there. And you also want to make sure that the water level is covering as much of the tube as possible. All right, in just a minute when we get the data collection software ready, then we're going to hit collect, and we're going to turn the heat setting up to about 250 degrees Celsius. Alright, over here on the lab quest, what I want you to notice is a few things I need to do. First, you'll notice that there's a glare there. It's annoying. Obviously, the first thing we need to do is change the units for the temperature scale. So just click in the red box for temperature and change units and hit kelvins. And we don't have the option to read pascals on the pressure. It's always going to read kilopascals, but we'll just have to keep that in mind later when we do a calculation. Now, the next thing we want to do is we want to go to Sensors, Data Collection, and we are going to make time-based measurements, but we want to change the interval to 30 seconds. And then the length of time, 90 seconds was okay, but 1800 would be better. So that should run for about 30 minutes. Alright, so now it's ready for collection. The next thing we want to do is display the graph that we're interested in. Since we're going to determine the universal gas constant, we'd love to see a pressure versus temperature graph. Right now you can see it's automatically gone to default of pressure versus time and temperature versus time. The way we can change that is go to Graph Options, and right here when it says X-axis column, we can change that to temperature, and then here Graph 1, Y-axis, change it from temperature to pressure. So now Graph 1 is pressure on the y-axis and temperature on the x-axis, which is what we're after. So we'll click OK. And then when we get to graph, we can say just show graph 1, since that's really the only one we care about. And so now we've got a pressure in kilopascals versus temperature in kelvins graph ready to go. And so we just hit the collect button, and it'll start collecting. It'll take one measurement every 30 seconds of the pressure and temperature at that point. So then we come back over here and turn it up, as I said, to about 250 degrees Celsius. I found that that was a pretty good heating rate for this amount of water to get good data. Now, what you want to be careful of as you monitor this is you want to make sure that the seal on the stopper on the test tube doesn't come loose. You want to make sure that's nice and tight before you start heating. And the way you're going to know if that seal breaks is obviously right over here. You're going to see your pressure drop back down to atmospheric. So just keep an eye on that occasionally as the lab goes. When it's done, then you're going to hit, actually it'll run its course, you won't have to hit stop. But then what you're going to do is you're going to get a best fit curve. Remember, you do that by going to Analyze, Curve Fit, select the graph you want, which in this case is the pressure versus temperature graph, and then fit equation, you're going to choose a linear fit, and then that'll give you the coefficient for that curve fit. Alright, and in a second we'll go over mathematically what to do with those numbers.
Alright, so now we need to talk about how we're going to calculate the gas constant with our data from our lab. Now, of course, something you'll want to discuss in your lab write-up is the fact that we are making a pretty big assumption that the gas in the tube is an ideal gas. So you'll want to consider that when you look at sources of error and your error discussion there. But for our purposes, we're going to assume that it's an ideal gas. And what that will allow us to do then is use this graph of pressure versus time. We divide both sides by volume, and we get this guy, which, as you can see, would give a linear relationship where the slope is this constant of the number of moles times the gas constant divided by the volume of the container. So once you get your best fit curve, your linear best fit curve, you take the slope and you're going to set it equal to this nr over v. So let's talk about how we're going to get that nr over v real quick. First of all, if you think back to chemistry, you'll remember that 1 mole of an ideal gas at standard temperature and pressure occupies 22.4 liters. Well, we're not at standard temperature and pressure. We are at standard pressure because it's about 1 atmosphere in this room, but we're definitely not at standard temperature. So the first thing we need to do is to find the volume that 1 mole of an ideal gas would occupy at our temperature and standard pressure. So to do that, we know the pressures are the same, and so we've got V1 over T1 equals V2 over T2. We can set that up as a ratio then, that V2 is going to equal V1 times the ratio of T2 over T1, just multiplying both sides by T2. Of course, the temperature in the room in kelvins is about 294, and you can get that exactly by measuring the temperature with your probe before you start. And then standard temperature is 0 degrees Celsius, which is 273 kelvins. So this ratio will tell me what I need to do to 22.4 liters to get it in the volume that it would be at the temperature in the room. And I worked that out earlier. I believe it's about 24.123 if I remember correctly. Liters. Of course, if the pressure we're measuring is in pascals, or in this case kilopascals, that's newtons per square meter. And so I can't use a volume of liters, I need a volume of cubic meters. And so I need to go from 24.123 liters to cubic meters. Fortunately, this is pretty simple. I know that 1 liter is 1,000 milliliters, and 1 milliliter is a cubic centimeter. Then I just have to be careful, remembering that when I go from cubic centimeters to cubic meters, it's not 100 centimeters in a meter. It's 100 raised to the 3rd power cubic centimeters. And if you think about that, right, if you've got a cube, if this is a 1 meter cube, that means that this dimension is 100 centimeters. So when I go to a cubic meter, then I have to do 100 times 100 times 100 for each of those 3 dimensions. And so that's where we get that 100 cubed to convert to cubic meters. And I believe, again, I'm going from memory from what I did earlier, I believe that gives me 0.024123 cubic meters. That then volume is the volume of how many moles? 1. So when I look at this, the slope is equal to nR over V. That ratio of N over V is 1 over that. So R equals the slope of the line off my best fit curve times the reciprocal of N over V. So the reciprocal of this, which is 0.024123. So all that to say, when you get the slope of your best fit linear curve off of your data from your pressure versus temperature graph, assuming temperatures in kelvins and pressures in pascals, oh yeah, we have to remember that it's going to come out in kilopascals. So this slope, since it's going to be in kilopascals, you're going to have to multiply the slope by 1,000 to get it into pascals. So don't forget to do that. But as a result, you take the slope times 1,000 and multiply it by 0.024123, and that should give you your value for R that you calculated in this lab. All right, do well.